is 3.4. So here we go. We're going to see how it goes. What button do I push? Wrong button. There we go. Okay, so 3.4 is limits at infinity and asymptotes. And they give you this graph on number 4, and they ask you to find the limit as x goes to infinity. So here's x is 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. And I'm not going to be able to convince you that that's anywhere near infinity. But you can see kind of it's asking you what's the y value. And it looks like if things continue the way they're going, right, it looks like that it's getting closer and closer. Do you guys agree? Kind of wrapping around. It looks like it's getting closer and closer to 2. And so what about if I go to negative infinity? So here is -1 and -2 and -3 and -4 and -5 and -6 and -7. So as I'm going this way, it looks like it's going under and then just kind of going up. Just to me, it just looks like it's going to go right there. And does that -1? So they're looking for what does it look like it's getting closer to. Now here's some other asymptotes, and we actually looked at these in chapter asymptote chapter, limit chapter, not asymptote chapter, the limit chapter, chapter 1, right? So as we get close to 0, so as I get close to 0 from the left, this looks like it's going to negative infinity, and from the right, looks like it's going to negative infinity. So this is negative infinity. As I get close to 2, but I stay smaller than 2, so if I stay smaller than 2, I would be on this side of 2, and that looks like that's going to negative infinity. And if I get bigger than 2, so if I stay bigger than 2, that looks like it's going to positive infinity. And so off the graph, you can really kind of see where things are going. Now it's asked to use some equations of the asymptotes, and we had already learned about the vertical asymptote, right? And these right here, we're talking about the vertical asymptote. So there's a vertical asymptote right here, right? And so there's the vertical asymptote, and it's a vertical line at x equals 0. So x equals 0. I always am asked, can I just put 0? And 0 doesn't tell me if it's a vertical line or a horizontal line or anything. You need to have x equals 0 so that I know that it's a vertical line. And then also at 2. So there's a vertical line right here, and they're asking me what is the equation of that vertical line, and that vertical line is x equals 2. And then the horizontal asymptote, and so you could kind of see here that as I got closer to infinity, this was kind of snaking around. And what was it snaking around? It was snaking around this line, and that line is y equals 2. So horizontal line. And also there was the asymptote here. It was snaking around, right? So that's a dotted line, and it was snaking around y equals -1. And then something just to note is that it's okay for a graph to cross the horizontal asymptote. It's where it's getting closer and closer to as x goes to infinity, the horizontal asymptote, and the graph can cross it. So you notice the graph crosses the horizontal asymptote here, and it also crosses, it looks like it crosses here, the horizontal asymptote. But the graph should never cross the vertical asymptote. So anyway, so just FYI on that. Then they give you some rules for finding limits, and so we're going to look at these rules. And so they say that let n be a positive integer and let p be a polynomial. So we have this as a positive integer, and this is our polynomial. And that's going to be used for this one, isn't it? So this first one is the limit as x raised to the n as x goes to plus or minus infinity. And so if this is even, so in other words, they're asking like the limit as x goes to, let's say, infinity of x to the second. So as I get close to infinity for x to the second, wouldn't you agree that that's going to infinity? And would that change if this was a 4 or a 6 or an 8? Well, it'll just be going faster, right? And what about if I'm saying the limit as x goes to negative infinity, that's where they were saying plus or minus. Now they said that this had to be even, the exponent. So let's say 6. And so this is a negative infinity, a really, really big number raised to the 6, right? So that's positive, right? A negative raised to the 6 is positive, so this is going to positive infinity. And so that's all that they're saying there. And I think that you could, I don't think that, I mean, it seems natural to me that that's what it would be. And so you definitely can memorize that theorem if you want, that they have there, Theorem 2.6. Now they say as x goes to infinity of x to the n equals infinity, and the limit as x goes to negative infinity of x to the n is negative infinity when n is odd. And that certainly makes sense too, right? Because if you have a 3 and you have a really big number, a positive big number raised to the third, that's going to positive. But if you have a really small number, right, negative of a really big number, which is a really small number, but a negative raised to the third is a negative. So it's be going to negative infinity. So anyway, I think that one makes sense too. And then as x goes to infinity, so now think about this, 1 over a really, really large number, right? Because if you put infinity there and you raise it to a power, and so 1 over, just to see what they're saying here, 1 over any constant over a really large number. So let's say a million raised to the 6th. I don't know if I have a million there, but whatever I have. And so that's 1 times 10 to the negative 42. So that is 41 zeros, point, and then 41 zeros, and then a 1, right? And so a lot of zeros, nearly 0. And if you get closer, maybe I'll take out some of these so that I can just have a whole bunch of zeros and not, and so that's maybe, those still won't fit on my screen, those zeros, right? Maybe these zeros will fit on my screen, S to D, there they are, right? And so, and that's not even, that's my base being only 10. They said, what if this goes to infinity? Well, look how close that already is to 0. Okay, so now 1 over x to the n is the same as x to the negative n, so they're just making that clear, that those are exactly the same. And it doesn't matter if you're going to plus or minus infinity, and it also doesn't matter if n is even or odd. This is very, very near 0. 1 divided by a very large number is 0. 1 divided by a very, very small number, negative, right? So negative large, right? So if I just turn this into a negative there, and it didn't matter, I have 6 here, so maybe I should be more careful and put parentheses here like this. So this is going to be positive, but even if I change this to a 7, it's still really, really close to 0. Even though it's negative, it's close to 0. So so that's why they're not making a big deal out of that. Now they're talking about your polynomial. So here's our polynomial. And they say if you're trying to find the limit of this polynomial as you go to infinity, then this is infinity or negative infinity, depending on what's going on with the leading coefficient, with the leader. So it's saying that this other stuff doesn't make a difference. This stuff doesn't make a difference. Look at this guy, and if this is going to positive infinity, it's going to pull the rest of it to positive infinity. Even if the rest of this stuff was all negative, it just won't go to a positive infinity as fast. And if this is going to negative infinity, it's going to pool. Anyway, so that's kind of the story on there. So people call that dominant term analysis, that number 4 there, that it goes to them. So we'll give a try to some. So here they're asking me to, this is number 30, find the limit, right? And according to number 4 that we just found, look at the leader, right? So this is the limit as x goes to infinity of negative x to the 4th, right? And so we don't have to look at x to the second and see what x to the second is doing. And as I go to infinity, this part is going to positive infinity and then negative times it. So this is negative infinity. And we used number 4 of the limit laws here, right? Number 4 of the limit laws. Okay. And then this one right here, the way they show you to do these in the book, because you're kind of like, wait a minute, they don't talk about having a polynomial, a rational expression like that in their limit laws. But what they say the strategy is to do is to divide every piece by the highest x that you have in the denominator, which is x to the 3rd here. So they say that you can divide every piece. So this is the limit as x goes to infinity. And I'm going to divide 1 by x to the 3rd. And I'm going to divide x to the 2nd by x to the 3rd. And I'm going to divide x to the 3rd by x to the 3rd. I'm going to divide x by x to the 3rd. I'm going to divide by x to the 3rd. And then now I can use that property that they had given me. Which number was it here? It was number 3, right? I have 1 over x to some power on all of these guys, right? And so I'll simplify these so that you can see that's what I have. So the limit as x goes to infinity. So this is 1 over x to the 3rd. So if I'm going to infinity, that's going to 0, right? And this is 1 over x, that's going to 0. And this is 1 minus, this is 1 over x to the 2nd, that's going to 0. And this is, I don't remember that one being that. It is, though. So plus 1 over x to the 3rd. So by number 3, right, property number 3, this is going to 0, and this is going to 0. So in my numerator, I have 0 minus 0. I have 0, right? And this is going to 0, and this is going to 0. So this is going to 1 down there, minus 0 plus 0, right? So this is going to 0 over 1, which is 0. Can't write it. So it's going to 0, and we used our property. Now there's another way of doing this problem, and I'm fine with either. And a lot of books show this. Our book didn't show it, I admit. And it's called dominant term analysis. And what dominant term analysis means is that you look at, and they kind of showed it, and it was kind of like number 4. You look at what the leader is in the numerator and the denominator. So they say that this is the same. So DTA, dominant term analysis, right? And we're going to infinity. And the leader in the numerator is negative x to the 2nd, divided by the leader in the denominator, which is x to the 3rd. When you reduce that, that's the limit as x goes to infinity of negative 1 over x. And that's going to 0. You guys agree? And so as x gets really, really large, you're dividing by some very large value, right? And so it doesn't matter if it's negative or it's positive. It's getting really, really close to 0. So we did a lovely job on that. Okay. So here they're saying, hey, if you were going to infinity, then what would this be? And you can use the dominant term analysis on this, because t times t to the 1/2 right here is t to the, so this is t to the 1 times t to the 1/2, which when you add the exponents is t to the 1.5, right, which is t to the 3/2. So this is the limit as t goes to infinity of t minus t to the 3/2 over 2t to the 3/2 plus 3t minus 5. And we can use dominant term analysis on this. We can also do that trick that we learned up here if you wanted, and you would be dividing by t to the 3/2, because that's the biggest exponent. This is t to the 1 of t's in the denominator. So I like to use dominant term analysis, works out quite nice. So this is the limit as t goes to infinity of the biggest guy in the numerator, which is negative t to the 3/2. This t to the 1, biggest exponent, and 2t to the 3/2. Those cancel out. So dominant term analysis means getting rid of this and getting rid of this and getting rid of that. And so this is negative 1 over 2, right, when those cancel out. And anyway, so going to negative half. And then I just added this question just because I was curious if we would be thinking or if we would just use dominant term analysis blindly. But if you're going to negative infinity, wouldn't have been too good because the square root of a negative, right? Can't find the square root of a negative. So you kind of have to watch them because sometimes they'll get tricky on you and ask you a question like that. Now, I'm always asked, so you could just ignore that? I mean, that was going to infinity, and you can just ignore that because that one's kind of bigger. And, you know, like the national debt, it's really huge. And it's like going to infinity is what it's going. It's really, really big. So if I said to the government, you know what, I want to help. So I'm going to send $5 to help with the national debt. It's $1 trillion, whatever it is. It's huge. Right? It's not going to make the news. It's not even going to change the numbers, as they've said that, you know, what the national debt is. I don't even know what it is now, but it was huge before, $9 trillion or something, whatever it is. My $5 is not even going to change anything. You're not even going to be able to see it when they round the way they do and whatnot. And that's what's going to happen. When I get into infinity, t is not going to make any difference. T to the 3/2 is going to take over, and 3t is not going to make any difference, and certainly the $5 right here, it's not going to make any difference as I get closer and closer to infinity. If you want to graph this and see, so put this all in Desmos and graph it as you get closer and closer to infinity, you'll see what I'm talking about. That when you're close, when you're talking about numbers like 8, and numbers like, you know, 9 and 10, you're not getting close to an output of negative half. It's when you get to bigger numbers, right? So when you get closer to infinity. And that's when this starts to make no difference at all. So there, ooh, are you going to focus, my friend? Okay. So on this one here, you can use dominant term analysis on it as well. You can also use the divide by x to the 3rd, but you have to be careful because when you're up here dividing, you have to know that you want to be dividing by, if you want to divide by the square root of x to the 6th, right, to make x to the 3rd. So, and then you have to be kind of clever as well. So I like dominant term analysis, I have to admit. And so what's the dominant term in the numerator? What's the biggest term? Well, and so I can ignore the other term. So by DTA, the dominant term in the numerator, hi Susie, are you here to do math? Is the square root of 4x to the 6th. and in the denominator is negative x to the third. And then this is where I have to be careful. What's wrong with you, girl? You tired of Mama making videos? I bet you are. I got this little cat, and she's so sweet. Okay, so the square root of 4x to the 6, here's something that I have to tell you. It's not equal to 2x to the third. And so you might think that it is, but it's not. It's equal to the absolute value of 2x to the third. And that's either equal to, let it be the same, 2x to the third. This is when 2x to the third is greater than 0, greater than or equal to 0. Or it's negative 2x to the third. This is when 2x to the third is less than 0, right? And you can solve that, and this is when x is greater than or equal to 0, and this is when x is less than 0. And so where was I going? I was going to negative infinity. And so is x less than 0 if I'm going to negative infinity? Or is it bigger than 0? And so, well, it's less than 0. And so when I take the square root, it's equal to the absolute value of 2x to the third. And that's a property that we often ignore in our algebra class, that the square root of x squared is not equal to x. It's equal to the absolute value of x. And why you think that it's okay is because sometimes they tell you x is positive. And if x is positive, then it is. You don't have to write the absolute value. But if x is negative, then you need it, right? And so anyway, so this is equal to negative. So I still haven't taken my limit yet. The limit as x goes to negative infinity. And then this is negative 2x to the third, because I'm going to negative infinity, over negative x to the third. So a negative divided by a negative is a positive. This is going to 2, right? The x to the thirds cancel out, and so I'm going to 2. So we did a lovely job on that one. And then I asked you the question, what if that had been going to infinity? Would that be a different problem, right? And I said, oh, maybe that would be something similar, would be a good exam question. So if I had been going to infinity as opposed to negative infinity, then I still would have said dta. So I said example, right? And I would have been saying, okay, the limit as x goes to positive infinity, and this is the square root of 4x to the 6th, because at infinity this doesn't make any difference, and neither does the 2. So just the dominant term in the numerator and the dominant term in the denominator. And the square root of 4x to the 6th is the absolute value of 2x to the third, right? And that's equal to, leave it the same, and this is if I'm bigger than 0, and certainly infinity is bigger than 0, so this is the limit as x goes to infinity of 2x to the third over negative x to the third, which is negative 2. And so anyway, so that's kind of that story there. Did a lovely job on it. And then this is number 22 in your book, and I have a typo on it, and I don't remember. Oh my gosh, are you kidding me, my friend? Okay, so I think my video camera is as tired as I am. And so find the limit or show that the limit doesn't exist. And one of these is number 22 in the book, and the other one is a typo. And so I made a boo-boo, and it can happen to you as well. And I don't remember which one is which, because I know that at first it was this one. It was the first one that was listed was the typo. Then I kind of liked the typo problem too, And so then so I did both in class, and then eventually they both have gotten there, so that I put the verses in between. So one of them is an example out of my head, the other one's from the textbook, but certainly they could have had either one of these problems be the problem. And so anyway, so that's my my story on that. So they have that dominant term thought, right? And so but here's the thing, is that if I have something that's big or huge and I subtract something that's huge, let's say, how do you spell huge? Is that a G and then an E? I hope. I don't know. Where's my phone to tell me if that's how you spell huge? Because I don't want to make a fool out of myself. Maybe I've already done it. Maybe I've already become a fool because I have to look it up. Why didn't I just use another word, like a big E or something like that? But it says extremely large or enormous. But here's the deal. When you take something that's big and you subtract something that's huge, in other words, they're not the same size, but they're both large. The answer isn't necessarily 0. Now, it might be 0 if they're close to each other in size, but it might be that this one's always a lot bigger than that one as a possibility. And so there's where the problem lies. Okay, but on the other hand, I could take something that's big and I can add something that's huge to it, and I can tell you that that's equal to infinity, right? If I get something really big and I add something really huge to it, that's going to be infinity. I can make it go. This is going to be the biggest, right? And so that's what kind of happens in this problem here. So when I start thinking about it, the square root of 4x squared, just looking at the dominant term here, the square root of 4x squared is equal to the absolute value of 2x, which is equal to 2x or negative 2x, depending on if 2x is greater than 0 or if 2x is less than 0. So since I'm going to a negative infinity, this is like being negative 2, right? And then when I put that with this, I can't say that's 0, because this really wasn't negative 2, so the 3x is really going to start to play a part on it, because this, because I'm going to negative infinity, isn't really negative 2, and negative 2 plus 2x is 0, because I'm kind of getting this idea that I have two things that I'm subtracting. They're not really equal to one another. This is clearly a little bit bigger than that. And so you really can't subtract them and say that they're 0, right? Because even though this was going to negative 2x. So it's getting close to negative 2x, but it's not quite there, and so this starts to play a part. So what you have to do is you have to multiply this, put this over 1, and multiply this by the conjugate. And when you multiply this by the conjugate, so I'm going to multiply here by the conjugate 2. So this was 4x squared plus 3x, and under there, 4x squared plus 3x. So when you do that, when you multiply this by the conjugate, then you get the limit as x goes to negative infinity. This was, I think this is the problem that wasn't really in the book, was really number 22. And I multiply, when you multiply by the conjugate, it's so that the outer and the inner will cancel. So the first gives 4x to the second plus 3x, right? And then this is minus 4x to the second. Now I can subtract these because this is really what it is. When you do dominant term analysis, it's like I'm rounding. and I'm saying this is about negative 2x, and that's 2x. Well, that's when you start to get the problem. But this is truly 4x to the second, and this is truly minus 4x to the second. And then down here in the denominator, I have 1, and I have 4x to the second plus 3x, and then minus 2x. And then now, how I've changed things, in the numerator, I have 3x. And in the denominator, by dominant term analysis, DTA, this is negative 2x and minus 2x. And now I'm not getting 0, so it's kind of this idea. I know that it's negative big plus negative huge is negative infinity, or negative bigger, or whatever have you, but I can add them together now because I'm not trying to say that it's 0. I'm adding two big things. And so this is negative 4x. So I'm okay to say this is about negative 2, because I'm not going to then say that it's going to subtract with that other thing and I'm going to call it 0. So this is 3x over negative 4x. And now the x's will drop out, and so this is negative 3/4. And so when I subtracted the big minus huge, that's what I had going on, it wasn't 0, it was negative 3/4. So they were really close to one another, but it wasn't quite 0. Over here, on the other hand, when I go to negative infinity, with this being a negative, then this here, by dominant term analysis, is very close to negative 2x. So this is very close to the limit as x goes to negative infinity of negative 2x minus 2x. And since I'm not going to call it 0, I'm okay to add them together. And so this is going to negative 4x, and this is in here, so this is going to 4. Oh, no, it's not going to 4. What am I saying? Going to infinity. Negative 4 times negative infinity is not 4. I'm pretty tired. It's infinity. And you're certainly welcome to go and look at a graph of this, if you like, or a graph of this. And I've been advertising the graph of those things, and so as if you should go and do it, and then maybe you will and maybe you won't, so maybe I will. So I'm going on Desmos on my phone, and I'm going to be graphing, and I'm going to put this in here, y equals, and then I'm going to do the square root of 4x to the second and plus 3x, and then I'm going to get outside of that, and I'm going to add 2x. And then where did we say that we were going? We were going to negative infinity, right? So here I am going to negative infinity, and I'm looking at the output. So every now and then we'll get on here and get the output. Oh, my finger is so fat that it's in the way. We can't see it. It's negative 0.75, which is very close to negative 3/4. Okay? And I'm only at negative 125, so I'm not quite to infinity yet. But I'm getting there, right? We're not even at the national debt. How come I can't do that? Andrea? Okay, so there I am at negative 0.751, right? And so as I go that way, I'm getting closer and closer to negative 3/4, like I said. Now, if I come over here and I edit this a little bit, and I put a negative in there, subtract, right, this one here. And remember, I said this one was going to infinity. So let's get over here and see if we can find the graph. So here it is, right? And so it's just, you can see that it's just going through the roof, right? And so I'm only at negative 600, and I'm already up here at, 2,880, whatever, and as I keep going up and up and up, as I keep going to negative infinity, right? As I keep going to negative infinity, it's just going higher and higher. It's going to positive infinity, like I said. So hot diggity dog. And so you certainly could look at those on a graph. So that sounds good. And then they tell you about the horizontal asymptote. And so this is what they're kind of getting at here. And the limit as x goes to infinity of your function, or the limit as x goes to negative infinity of your function, gives the horizontal asymptote of the graph y equals f of x. So here, so we want to look at that. They say find the horizontal asymptote, and they're wanting us to write out what we found. So how you find the horizontal asymptote is you look at the limit as x goes to infinity of this function, 2x to the second plus 1 over 3x to the second plus 2x minus 1. And by dominant term analysis, DTA. Remember that I was telling students how to do this. I mean, I had been teaching calculus a really long time, and there was a really, really nice man over in the math lab who tutored people in our math lab in his retirement, and he had been a math teacher for, I don't know, 30 years before that, and probably tutored for us for 30 years. I mean, like he was 80 when he retired or something. Really nice guy. And I don't remember what I called it or whatever have you, and he called me on the phone and he said, Donna, they call it dominant term analysis. I'm like, oh, it had a name. I've never seen a name of it in a book. And so, anyway, so the 2/3, right? X to the second over x to the second. So as I go to infinity, I'm going to 2/3. And actually, you could repeat this whole story, the limit as x goes to negative infinity. And so that you could have this whole thing here, and it's going to be this, right? So quotes, right, saying equals 2/3. So it didn't matter on this one if I was going to positive infinity or negative infinity. Sometimes it matters if you're going to positive infinity or negative infinity, and you might look back on ones where it seemed to matter whether you were going to positive infinity or negative infinity. And so I was just kind of looking at this one, just drawing it out of the thing, right? When I was going to negative infinity, I got 2. When I was going to positive infinity, I got negative 2. And so it mattered on that one. And anyway, so on this one it doesn't. It asked me to find, so this is the vertical and the horizontal. So the horizontal asymptote is y equals 2/3. So horizontal asymptote, right? And then the vertical asymptote, we found the vertical asymptote in chapter 1. And do you guys remember what we were looking for to find the vertical asymptote? Yeah, you're looking for when the denominator is equal to 0 and it can't be a common factor with the numerator. Well, the numerator doesn't factor, so that's good. And so I have to factor the denominator in order to find where it's 0 or use the quadratic formula. And I'm hoping that you'll just factor it. And so, and how I factor it, I was just going to factor it out there, and then I realized that maybe we should practice our factoring. X times 3x squared, make the first work. 1 times 1, right? It has to be a plus and a minus. So I use unfoil. You can use whatever you want. And so let's see here. This is x, and this is a 1, and this is a 1. And now I have to fit in here a plus and a minus, and I want it to get 2. And I want it to be positive 2. So I think I got to put a plus there and a minus there so that I get positive 3x minus 1x is positive 2x. So I'm going to get x equals positive 1/3, right, if I add 1 and divide by 3, and x equals negative 1/3. So these are, and those don't make the numerator 0, right? And so the numerator really didn't factor. And so these are the vertical asymptotes. And I can put them on the graph over here, verify with the graph. So we're saying that we have, at negative 1, we have, I feel like I don't need to use my ruler, but, you know, here I am using my ruler. Here I I am at -1, and I'm going to draw in the vertical asymptote, doink, 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 dotted, right? And I'm here at 1/3, so 1/3 is precisely right there, and I know I'm the most accurate grapher in the Bakersfield College math department. People, we have contests, you know. And so I graphed the vertical asymptote. Now I'm going to graph the horizontal asymptote. It's y equals 2/3. So that's a horizontal line right here, precisely here. And don't forget that the graph might cross the horizontal asymptote, and so it does cross it right there, and so anyway, so pretty good. I did a pretty good job at drawing it on there. Okay, I'm gonna give myself A+ on that. Oh, hot diggity dog. Okay, that's 3.4.